So, hi everybody, it's Tuesday again, and we are moving forwards with our AI for Pathologist summer school. I hope it's not hot for you wherever you are, but definitely it is summer. So, this is the first session, and in this session, we are going to do a huge jump from classical deep learning to the latest and greatest. We are not today. We are going to discuss, I would say, the foundations of things such as ChatGPT and all the I would say that mainly all of these things which bring amazing capabilities to AI and deep learning. I really gave some thought. I have like the light version of this session and the heavy session. The heavy session would take much, much longer. And it's full of mathematics. And I don't know how much you are here keen about mathematics. So again, I think that the aim for me is to try to convey, I would say, the intuition and the message rather than going into the details, which are also super interesting, but I think that are maybe belong to another course which is more into the mathematical details of all of this. Again, I will be happy if you want to ask any questions in the middle or send me an email afterwards. I will try to do my best to answer. So let's start with sharing my screen. And I want to share this and this. Okay, so transformers and foundation models. I guess that these two terms you somehow heard. Foundation models in pathology are now really super hypey, and everybody's talking about that. We also talk about that, and we also look at ways to integrate foundation models into what we do. So yes, it's super hypey. But how did it start? What is it? What does it do? And how does it work so well? And why does it hallucinate? So in the first two sessions, we tried to understand and to figure out how classical deep learning neural networks work. So I hope that by now you got some, I would say, a general idea that we have capability to extract features. These features are facilitating the process. And at the end of the process, we make some decisions. And our decision making is improved and improved and improved by the iterative process, which we call this iterative process the learning. We have the learning phase of the deep neural network, where we set all the parameters of the neural network. And if you recall, we discussed that we are measuring here some loss function, and this loss function affects all the parameters via backpropagation and back and forth. Sammy, shh, I'm sorry, this is my one of my dogs, and he will be quiet soon. He didn't get his medications yet. Samumi, bo. Okay, some attention. This is my dog is suffering from anxiety attacks, and as it's really it's a great dog, but he needs a lot of care. Okay, so let's hope that Sunny will be better for the rest of the session. So this is the classical I would say structure of a deep neural network, and the components, the very basic component of a deep neural network is some kind of a node where all the data is entering getting some weight, and we have some kind of a weighted sum, but we also have an activation function, which means that we don't account simply for the weighted sum. We want to see that this weighted sum is really meaningful so that it crosses some threshold, and only then it continues to contribute in our deep neural network. So this is Bobby. Bobby is not with us anymore for the last 2 years, and I used Bobby's image as an example to talk about classification problems. Classification problems, we just want to get the general idea what's inside this image. We don't care where the dog is, how small or big it is. We just want to know that there is a dog in the image. Then we talked about semantic segmentation. Semantic segmentation, where we want to segment an image to various regions. Object detection gives us localization. So we have some bounding box around the objects in the image, and we also know what's inside each object. And instant segmentation, we get localization. We know where each object is located, but we also get the specific boundary of each and every object. So in computer vision, this would be like the main, I would say, tasks that we use or we used to use deep neural networks such as Mascar CNN and UNet and you name it. I mean, these are the classical things. And something big happened in the last 2 or 3 years, where alongside these models that we have discussed, amazing new tools became available. Now, in order to actually give you some understanding of what these tools are, so we do need a little bit of mathematics. And I want to get started with a very interesting creature called autoencoder. Now, what's this nice diagram? We have here input and we have here output. Autoencoder does a seemingly super silly task. The silly task that an autoencoder is doing is to get X and to get back X. So we get X as the input and we want to have X as the output. So what's the point? That doesn't make any sense. I mean, it does. Well, now let's figure out why. We have here one neural network, which we call the encoder. We encode the information of X into some feature space. So this stage actually aims to figure out how we can represent the information inside X. Okay, when we train this part, we really try to like, what do I mean when I say feature space? It means that like in language, it would be to have the different letters and pronunciations and maybe the rules. In images, it would be the edges and the, I don't know, and patterns, like basic patterns. So I want to have a way to extract this information. And then the decoder looks at this vector, which we call the embedding space or feature space. So it looks at this feature space and it tries to build from the presentation that I've made, it tries to build back exactly the same input. And how do I train this autoencoder? I look at the error and I want the error to be minimum. I want X hat and X to be as similar as possible. So here the loss function would be the difference between X and X hat. And when we train this, we get parameters which excel in two things. The parameters of the encoder excel at extracting the most meaningful information in our input data. And the decoder excels at taking this representation and being able to build the same information from it. So this is what an auto encoder does. Now, these two guys, these neural networks, so you didn't have to invent anything new. You are taking just one standard neural network, and you take one for the encoder, take one for the decoder, you stick them together like this. So we have the original image. Again, this is something that we already know. These convolution layers, the fully connected layer. And so we squeeze the information into a meaningful vector and create a new one. Now, why can this be interesting? It can be interesting, for example, for a very practical reason. It can be interesting to try to find abnormalities or anomalies in data. In standard, in classical neural networks, we can train a neural network to distinguish between dogs and cats, between tumor cells and, I don't know, lymphocytes, etc., etc. But what if our problem is a bit different? What if our problem is to say, this is normal versus this is abnormal? Now, how can we do that? If we give this structure, the autoencoder, a lot of normal examples, then what would the encoder learn? It would learn to have the features which retrieve normal patterns in the best way. So the parameters of the error would be minimal when the input is normal. Now, when we insert into this autoencoder information which is abnormal, then, I mean, the parameters are not tuned to retrieve information which is abnormal. So what would happen? The error, the loss function would be higher. So we don't train, we don't even have to know what kind of abnormalities we may face. As long as we know what normal is, we have an indication that the data that we were just given is not normal. And this is like a beautiful example of anomaly detection using autoencoders. Beautiful practical example, but I will go back to the term of autoencoder more and more as we progress with foundation models and with transformers. So I hope that, well, I see there are no questions by now. Sunny is relaxed. I have to pet him because he wants some attention. And as you will see, attention is all you need, is the name of the most important paper for transformers. And I think, I'm not sure that they thought about attention that your house dog needs, but definitely house dogs need that as well. So I think that there is more depth in this sentence than I thought at first. But if in the 60s of the previous century, the Beatles said that all we need or all you need is love, then in the 20s of our current century, attention is all you need. So it sure is correct for transformers, but as I said, this is you can take this slide to more philosophical directions. So, okay. So a typical neural network we already saw, input, output, we are trying to find something. But another problem which really drew a lot of attention already for a very long time, but definitely since the beginning of deep neural network, was the problem of translation. Translating from one language to another. Now, if you are old enough to remember how things were working like 10 years ago or even more, terrible. Terrible, terrible, terrible. I mean, the translation, if you translated I don't know, from Hebrew to English or and vice versa, you would get like super silly sentences. And this really improved dramatically. Now, what's the problem with using deep neural networks for translation? Well, the problem is that if you do it in a very simple manner, then you have one word, and you want to train it, you want to train a neural network to translate this word to another word. Word number one, word number two, no, word number three. But, you know, a sentence is not really a collection of words. The words are there with a specific order. They are related to each other. So there is some connection between the words that make up a sentence. So how do we address these relations between the words in a sentence? And the first effort for that was with a methodology called recurrent neural network. And the name really implies how this is working. So basically, we have an X, we have this RNN, and you have an output and Y. So, okay, input, output, something in the middle, we already know that. But the point is that when this is happening, not only that it provides an output, it also keeps what we call an internal state. And this internal state captures the current and previous information, and we give this as a gift to the next phase. So this is how it looks when we unroll that. We try to think about a sentence. So we have the first word, blah, 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 something is happening, and we create the first translated word. But also the result of what happened here will become another input to the process when we inject the second word. So when we inject the second word, we don't look at it as a standalone word, but we also see what happened in what was the previous word and how it was translated. And this is how we create connections between inputs and outputs, because here each input was addressed independently. This is a dog, it's a dog. This is a cat, it's a cat. Here we have something which contains things which are related to each other. Now, the point is that each process of RNN is really a neural network that you have to train. And the parameters would not change when you go from here to here to here. So you're not like trying to train, many neural networks. You have the RNN, which is a single neural network, and it has to work well for X1, X2, X3, etc., etc. So this was called recurrent neural network. Here is a little bit of scary mathematics. This is a function. We have the current state, the current input, the old state, so what happened before, and this actually, we have a function that creates a new state. And this is how the information survives from iteration to iteration. So we have here H0 with X1, then we have Y1 and H1 and X2, etc., etc. So this is the main idea. And when we look at that, so as I said here, we have the same parameters, the same function that we use for RNN. And when we look at the entire process, so you can imagine that for each output, we can determine a loss function. Okay, so because we know what would be expected in the place of y1, and we got a prediction, so we know to calculate the loss, and also for y2, etc., etc. And again, we don't look at these losses individually. We look at the entire loss of the entire process, and we want to back propagate this entire loss into the system. So we have a bigger system which accounts for a sequential event with many losses, but it tries to optimize this thing in its entirety. Okay, so I'll skip that. It's not so interesting. Now, why RNNs did not survive that well? Because they were pretty bad when it came to remembering long sequences and long sentences. And this is really the first works with that were already like 12 years ago. And I think it's amazing to see how things really evolved. And there are some points where there is a leap in understanding. But this was a very, very important lesson, because somehow the optimization process using this architecture did not survive. We call this the problem of vanishing or exploding gradients. It means that the propagation of the loss function at some point either died or explode. So this is a problem, and the people were looking for alternative solutions. Let's see. Oh, so Nazish, thank you for your question. So Nazish just asked, why do we backpropagate the entire loss into the system? And so great question, thank you. The reason for that is that, let me go back to the slide. Yeah, it's because we use the same set of parameters, then it doesn't make sense that we will do some update with this loss and then change with this loss, but maybe it will then maybe it will be contradicting to the changes that we have done here. So we have to look at the accuracy of this process as a whole. And this is why we look at the loss as a whole. Now, it's not like, it's not sacred. There are many ways to calculate losses, but this is considered to be a pretty solid one. So I do hope I answered this question. Thank you so much for this important question. So the next phase after the RNN, hey, Diana, you are raising a hand. So you want to ask a question, or please go ahead and write it in the chat or in the Q&A. I will be super happy to try to answer your question. Okay. This is fun today. Thank you. A mistake. Why a mistake? By the way, I have some nice news for you. Maybe we get to meet each other in September, but let's see. Okay. So the next stage was LSTM, and LSTMs were intended to really solve the problem of the short memory of RNNs. And you see from the name, it's long short-term memory networks. And by the way, this term comes from electrical engineering many years even before AI. And so we have here a more complex structure. And the idea is that in RNNs, we had like the RNN, and we had input, output, input, output. Here, you see that the structure here is a little bit more complex, but we have a consecutive structure. And at each point, we are trying to predict the next output. And also, you see what's very important, that we have some kind of connections between each previous stage and the next stage. Now, I will not go into the details of what this hyperbolic tongueness and the sigmoid, etc., etc. There is a logic in here. I can assure you that. Although I think it's a mixture of magic and logic. But I think that intuitively, and it's not accurate mathematically, but I think it's accurate intuitively, we have here two channels. One channel would be responsible for the short-term memory, and another channel would be responsible for the long-term memory. And basically, why do I say that this structure is more complex? The reason is that we have here all of these things, and very, very roughly, they can be divided to a forget gate. This means that I tell the system at this stage what you can forget, what is from the past, what's more important, and what is less important. And this is something that you can learn. So what do you need to remember? This is super, super important. And then the input gate would say what is the meaningful input that I want to put in this process. So what I could forget. Now, how do I account for the new inputs? And then finally, how do I create the output based on past plus input? So this is a little bit more complex process, and we have some degrees of freedom where we can basically look at how the process goes. Okay. Now, LSTMs were a little bit better than RNNs. It did not, I mean, you can still get a problem of gradients vanishing or exploding, but this model is more robust for long distance dependencies. So there was an improvement, and this was great. Improvements are always great. Still, we came one step further, but we still have to go. Again, you see, this is work from 2016. There are some famous names here, like Jose Bengio, which is considered to be one of the godfathers of AI. And this paper, which is called the Badanu method, they again tried to tackle the problem of translation. And they tried to take it one step further. And I think that it is true that the paper Attention is All You Need got a lot of respect and rightfully. But I think that this paper is super, super important. And why is that? Because in principle, the usual way that translation was done was to take all the input words and go through the RNN structure or the LSTM. So to extract the structure of the input sentence, take all of this. I mean, you are looking at the dependencies, so you are learning how to structure sentences in one language. You take all of this understanding into the context vector, which is like the embedding space, feature space. Okay, you take all of this information, and from that context vector, you are able to create a new sentence in a new language. So the idea was, let's look at the entire sentence and grasp the information and create a new sentence. And what Badanu et al. Did was something which was much, much more sophisticated. And this slide I'm going to spend a few minutes on because I think it's very, very important. It's not a transformer yet, but it really captures, I believe, the essence of how transformers work. And I think that it's in my opinion, and it's only my opinion, of course, I think it's more intuitive than the structure of real-life transformers. So let's pay attention here to this slide. What do we have here? we have X1, X2, X3, etc., etc. So consider that as words in a sentence. Okay, great. So usually what we would have is to have this part in blue. So we have here like RNN or LSTM, and these are the internal states, and we are learning to do the connections, etc., etc. So they added something something very clever. They said, well, it's a sentence. A sentence is not mathematics where you have to, the order in sentences is super important, but when you look at the logic in the sentence, it could be that the last word also impacts the first word. I mean, it's not like 1, 2, 3, 4, 5. It's a bit different. It's more complex. It's richer. So why don't we look at things also the other way around and try to figure out how to build a sentence on the opposite way? It gives us more insights and more information. Okay, so and then after we do that, we train this. We try to teach this thing, and then basically we want to have we get some kind of a internal states, and from these inputs we get a lot of outputs, but then we don't use all of these outputs from this process, from this block. We don't use all the outputs as equals. No. And this is where the term attentions comes to life. It means that we are telling ourselves the following. Maybe this guy, this process is more important than this one, and this is more important than this one. So we try to provide some importance metric to each and every part in this process. Now, again, I'm not going to really go into the mathematics here, but what you can see is that we have all of these inputs, which are summed together. And in this summation of H1, H2, H3, so H would be some kind of a combination of the red and the blue ages. And we see that each contribution has a weight. So the contributions of each part in the sentence are not the same. Let's say, he is a nice boy. Okay, so I would say the essence of this sentence is nice boy. I mean, he's a boy and he's nice. So we try to think about sentences which are very complex, and we want to really say, yeah, but this is the important part of the sentence. This is the essence of the sentence, and maybe the other words are less important. So we are trying to figure out what's more important and what's less important. So we have a weighted sum and we have weights. Each weight means the attention that you give this part. And once you do that, we have here, so this is the encoder. This is where we encode the information from the input sentence. But take a look. We also have here the decoder. And the decoder, what we've seen before is that we gather all the information from the input sentence. So we have the context vector, and then we do the translation. Here it's different. In order to predict each and every word in our translated sentence, we are using the input again and again and again. So we have the translated sentence, we are building it. So to predict the next word, we rely on the previous word in the same structure of RNN, LSTM, etc. But we also account for the input coming from the original sentence, and we put it in again and again and again, and it's not the same for word number 1 and word number 2, because okay, so we will talk a little bit about mathematics. The weights here are, and this is also, are dependent on the internal states from the encoder and the internal states from the decoder. So there are two interesting mechanisms here. One mechanism is what we may call self-attention. Okay, self-attention means how the sentence is related to itself, how the input and the output sentence, how they can be built. Okay, so these are two processes here and here. But in order to understand how each and every word in the input is affecting each and every word in the output, we build a weight or an attention factor that accounts for each and every word in the input and the relevant word now in the output. So this is a more complex structure, much more complex structure. First, we look at things back and forth, one. But the second thing is that we are building the translated sentence in a gradual manner, and each time for the next word, the input, the attention that each and every input word is providing is different. And this is again super important. And this mechanism of attention, I would say, is the basic and most important concept when we talk about transformers. So here you have the two mechanisms side by side. I want to be very honest with you. This is a complex idea. It's not simple. It's not simple in any way. But I believe that I believe that it can be explained intuitively. I hope that you get the picture. I think that this slide is the most important one for understanding what transformers are, but we didn't get into transformers yet. So if you have, I hope that you got the point and you can intuitively understand what you see here. I will continue, and if you have any questions, again, feel super free to ask. Okay, and then a few years later, all of this very distinguished group of people created the paper, Attention is All You Need. And their concept was super simple. If we know in the process of generating new inputs, if we know how much attention we have to put for each and every word or structure in the input that we have, then we have a very strong mechanism to create sentences that make more sense, and then from these sentences to make paragraphs, and from the paragraphs make entire manuscripts, articles, whatever we are seeing nowadays in ChatGPT, Gemini, etc. So I think that the ability to analyze sentences and understand what's important and what's not is really a basic capability. And when you look at entire texts, you actually do scaling up of this basic capability. So the mechanism that they actually provided was the mechanism of transformers. And in transformers, what we actually do is, again, and again, there is the value and the key and the and the query, and I mean, we can spend 2 good hours only talking about that, and I don't plan to do that. Again, we have inputs and we want to get outputs. And in this process, what we are trying to do is we try to figure out what's important and what's not important for generating Y1, Y2, and Y3 from X1, X2, and X3. And the way that we do that, we use a mechanism of self-attention. We want to figure out how the inputs are related to each other, how each component in the input is affecting another component in the input. So this is one thing. And the other thing is that we are looking for connections between the inputs and the outputs and try to figure out how they operate. Now, all of this structure is the basic of a transformer. It's called, this structure specifically is called self-attention, because this structure mainly involves the attention coefficient of the vector x with respect to itself. And what the authors of the attention is only need the article actually found out is that when you take inputs, you are applying the self-attention mechanism to it. You have some kind of a machine learning neural network to process that. And then you have some normalizations. It's a very, very strong structure which analyzes the relations within the components of the input. And if you are sticking such basic components together, you are creating very powerful neural networks which have billions of parameters and are able to process very complex information. Now, I think that it is one of the difficulties, I think, in understanding models or trying to understand models that have 7 billion parameters. By the way, this, like today we were discussing in some discussions that we had some models that we are using, and one of our team leaders discussed that is using for a demo that we have 7 billion parameters a model. And yeah, but when you come to think about it, it's really difficult to understand how these huge models are operating. As a mathematician, I think that it's easier to try to understand basic concepts and to extrapolate, in the sense that when you are having a strong basic concept and you are just gathering a lot of these guys together, you have a very strong machine that can account for a lot of delicate and profound information. Now, again, the use case for the transformers and the attention mechanisms was to basically build from a set of inputs to have this mechanism of the recurrent neural network, LSTM, etc., to have some kind of weights and to inject these outputs into the, this is, I think, an example from English to Spanish or something like that. So, and to inject this information to generating the new sequence, and also to account for these words in the output, they will also relate to the inputs. So I think that basically transformers conceptually, I think, can be understood when we look at the work of Badanu et al. In transformers, I think that the ability to extrapolate and to scale was gigantic. And this is how eventually we are taking this guy, which is called the self-attention layer. We want to build from X how the weights and the values which will affect the output. And having this basic structure is the transformer. And when you are taking these structures, you take a lot of these basic structures, you get a super powerful machinery. Now, I will stop here because otherwise I have to dwell into like 4 hours of math, and I do that from time to time, but it's really, really very exhausting, and I think that eventually I think that the message should be simple. We have a mechanism that can look at relations within information, and based on that, we can produce new information. But all of this is pretty good, pretty interesting, pretty nice, but it is about words. In the world of computer vision, pathology, radiology, just good old image analysis, we don't speak about words, we speak about images. And I think that until 5-6 years ago, the world of language processing and documents and starting to have tools such as ChatGPT, etc., it was progressing amazingly, and the world of computer vision still remained in the classical deep learning era. But at some point, the computer vision people said, well, these guys are doing amazing things. Let's try to take some of the tools and try to deploy them into image analysis. And this is exactly what they did. So the concept of vision transformer came to life, and it is used as a building block to better understand the relations within the components of the image. Okay, but now I'm a computer vision guy or girl. I'm not an expert in LLMs. How do I do that? So what there is a joke about mathematicians that there are a few things that they know, and when they have a new problem, they try to translate a new problem into a problem they already know how to solve. Now it's a joke, but it's basically it's pretty true. So what computer vision people did was to take an image, divide it or break it into patches, and so the dimensions of the image, pay attention, it's like the original image is 224 by 254, and the three is like the three color channels, okay? Because each RGB, each color, basic color has a channel, and we have like 3 images stuck together to create a color image. Otherwise, we have only a grayscale image. So we break the original image into patches. Here it's patches of 16 by 16, okay? And then what we do, we flatten these patches into vectors. Now, vectors are one-dimensional creatures. And this is like something that I didn't tell you before, but you can imagine that when you do analysis of words, the neural network does not see a word. It sees a vectors of numerical entries. And I skipped before, and now it's a good time to go back. You see that here I didn't say anything about this word, embedding. Embedding means taking a word and translating it into a number. Now, you don't do that just, in a very, I don't know, without any structure. And there are mechanisms to accurately translate words into meaningful numerical vectors. What does it mean to have meaningful numerical vectors? Try to think like we have two words, king and queen. King and queen, I mean, they have more or less the same meaning. It's mean like royalty. One royalty is masculine and the other royalty is feminine. But it means that when we present king and queen as two vectors, we want them to be close to each other. We want these vectors to, not to be the same, of course, but to be close to each other. So there are a lot of mechanisms to take words and translate words into meaningful numerical values. Here, we already have the numerical values because images, digital images, are composed of numbers. And these numbers are super meaningful because they are containing the values of the gray levels. But it's not the only information which is important in images. In images, we have structure. And structure means that the position, the location of each and every pixel is also super important. And we can also account for the positional encoding. This is called positional encoding to account for the position information of these vectors. And now we had an image as an input, and we get meaningful numerical vectors as an output, and then we can use the transformers mechanism for not only for words, not only for translation, not only for creating texts, but also for analysis of images. Now, in images, there are many things that you can do with images. You can do a video and image generation. So, I mean, with tools such as nowadays, you have tools like you can write a sentence. I want to have I don't know, I want to have a white dog eating pink ice cream sitting on a brown chair, okay? And then we get an image. And we will discuss diffusion models, not today. But of course, when we talk about not only reconstructing new information, but we want to analyze new information, and we want to be able, for example, in pathology images, we want to be able to find structures and cells and all kinds of tissues, etc. And in order to do that, we need to understand, we need a mechanism that understands what there is in the image. And these mechanisms, what they do, and we discussed it before, they are extracting some kind of an embedding space, a representation which captures the essence of our data, and in that case, captures the essence of our image. And the concept of attention, together with the capabilities of transformer to understand relationships, these are a super important building block in foundation models and in many other things. Now, let me take a look at the time. So we still have 5 minutes to go. So I think that it's, I will make a pause and take a sip of my mitzpetel. It's a soda with some kind of a very, very unhealthy sweet construct of something very nice. Okay, so I will give you some opening words for the concept of foundation models that will be together with diffusion models. It will be the main topic of our next session. So foundation models were born only 5 years ago. Only 5 years ago. It's really unbelievable. They were born in Stanford. And I think that around 2021, we started seeing the revolution, which we all enjoy today. I think that nowadays we all use AI tools for almost anything that we do, for structuring texts, for a consulting, for I don't know, whatever. And I believe the sky is the limit. Although I think that the struggle that we may have in the future is to maintain our human thinking capabilities, and not tell my ChatGPT or my Gemini or whatever, my Claude, to talk to the other guy's agent, etc. And so you see that already when it started talking about foundation models, they talked about both opportunities, but also of risks. I think the main risk is that we lose our capability to judge things. So foundation models are huge neural network models having zillions of parameters. Usually they're the basic building block of foundation models would be transformers. And indeed, foundation models, again, they came from natural language processing. And the idea is that you are taking a huge model, you train it on a lot of data. And when you train it on a lot of data, so in some of you who are maybe active in creating AI for pathology, you know that one of the most annoying tasks is to do annotation. So if you want to train on like billions and millions of slides or data or words or text, yeah, it's going to be super tedious to do all of these annotations. So for foundation models, special techniques were built so that we are able to learn from unlabeled data sets, so that we can make this process not dependent on the human knowledge. I will explain in the next session how this magic is being done. And eventually, when you do that, you are getting a very big neural network that takes a lot of time, a lot of data, a lot of electricity, a lot of GPUs to train. But when you have it, then you can hand it out to other people and they can use it much, much faster because they have a model that was already trained. And the better the model is, that better it learns the structure of your data. So basically, and I want to finish with that, a foundation model is a very neat way to obtain the embedding space that we saw before. Yeah, you remember the autoencoder, the encoder, embedding space, decoder. So you can think about a foundation model, about this giant guy where you are training the entire thing. But then eventually you are getting from the foundation model the representation of your data, and then you can take this representation of the data and do amazing things with that. So we will speak more about foundation models in general, about foundation models in pathology. I know it's been a bit rough because we are speaking about state-of-the-art concepts, really a lot of mathematics. I do hope that you were able to obtain the intuition and the essence of the idea. This recording, of course, will be available. We'll be super happy to try to answer any questions. And I really want to wish you a pleasant rest of your day, and keep safe. Thank you very much. Oh, Jacek, how are you? Yeah, well, looking forward to visit Australia as well. Thank you very much, Nazish. I really appreciate your kind words. I sincerely enjoy this, and um, I think what's nice in our fields, because I think that this is like the fourth or fifth time that I gave this AI for pathologists a course, is that our field is progressing so fast that I can never be bored. We all have to keep up and learn. Maybe this is the greatest punishment of living in this era. Um, we have to keep learning. Uh, it's tiring, but I think it's also super important. So I will say good evening. I'm going to rush to the gym to do training also for the body, not only for the brain. Take care, guys. Bye-bye.